The paper is Thinking with Geometry, Active Geometry Integration for Spatial Reasoning, and it's introducing a framework called GeoThinker.
Right.
And the core problem here is, well, it's that existing multimodal LLMs are really failing at spatial intelligence.
Things like 3D understanding, relative positioning.
Yeah, exactly. It's because they rely on something called passive fusion. Basically, they just indiscriminately mix geometry features with visual tokens.
Which just creates noise and semantic misalignment.
Right.
So the solution they're proposing is active perception. Instead of that big global feature dump, GeoThinker uses Spatial-Grounded Fusion, or SGF.
Okay, and the mechanism there is what's really cool. The model uses its semantic visual priors to sort of query the geometry it needs.
Exactly. It uses frame-strict cross-attention. It effectively polls the geometry data only when and where it needs it.
And the results are serious. It achieves state-of-the-art on VSI-Bench with the score of 72.6.
And it outperforms proprietary models, like GPT-4o and Gemini, on the VSI-Bench for spatial temporal tasks.
Plus, it shows superior generalization in downstream tasks. Things like embodied referring with RoboRefer and autonomous driving with NavSim.
The takeaway is pretty clear.
Yeah.
Moving from geometry as input to geometry as demand is, I think it's the paradigm shift that we need for next-gen spatial intelligence.
Okay, take a breath. That was the 1-minute sprint.
Okay.
Now, welcome to AI Paper Podcast.
Juggles.
It's Thursday, February 12, 2026, and today we are unpacking a preprint that, it just dropped yesterday.
It's brand new.
We're looking at thinking with geometry, and if you're an ML engineer who's been wrestling with why your VLM can describe a beautiful sunset but then walks into a wall in a simulation, this is the paper for you.
It really, really addresses the elephant in the room.
Yeah.
We've spent the last few years marveling at these vision backbones, QuenVL, LV, even the early GPT-4 vision stuff.
And they're fantastic at semantic description.
Absolutely. You show them the kitchen, they can list all the appliances. But you ask a spatial question, something a toddler could answer.
Like, is the coffee cup to the left or right of the laptop?
Or, if I walk forward from here, am I going to crash into that table? They often fall apart.
It's that difference between knowing what is in the room and knowing where it is. I see the paper calls the status quo passive fusion. That sounds lethargic. What's technically happening in these older models?
It's essentially a brute force approach.
Yeah.
So in a standard setup, think VG-LLM or VLM3R, you have your vision encoder.
Right.
And then you have a separate geometry encoder, usually something like VGGT. That's the part that extracts 3D cues, depth maps, surface normals, that sort of thing.
Okay.
In passive fusion, they just take all those extra features and inject them into the input stream. They either, concatenate them directly or add them to the visual tokens before the LLM even sees them.
They're just dumping all the 3D data onto the pile and basically hoping the LLM figures it out.
Precisely. And the paper uses a great analogy for it implicitly.
Yeah.
Imagine you're trying to listen to a friend in a crowded bar.
Okay.
But everyone else in the bar is shouting random geometric coordinates at you.
That sounds like a sensory processing nightmare.
It is for the model.
Yeah.
It causes what they call information redundancy and texture misalignment.
Right.
Think about it. If you're trying to figure out where the sofa is relative to a bike, you do not need high-fidelity depth data for the blank wall behind them.
Or the flat floor tile.
Exactly. But passive fusion forces the model to process all of that geometry equally.
Which just creates a ton of noise. The signal-to-noise ratio must be terrible.
It's awful. The model gets completely overwhelmed by geometry data for pixels that frankly don't matter. And this explains the hallucination problem, not just factual hallucinations, but physical ones.
That's getting confused.
Yeah, the texture of the geometry features clashes with the semantic visual tokens. It's trying to read the text of the image, but the geometry is scribbling all over the lines.
So enter GeoThinker. The paper calls this a shift to active perception. That sounds much more, agentic.
That's the philosophy. Instead of being force-fed, the model gets to eat what it wants. It should only look at the geometry if it needs to.
And how does it do that?
They achieve this through a new architecture block they call Spatial-Grounded Fusion, or SGF. And for the Transformer heads listening, this is where it gets really interesting.
Yeah.
They don't put this at the beginning. They insert these fusion blocks into the LLM layers themselves.
Let's unpack that SGF mechanism. How does the model technically figure out what it needs?
It leverages the attention mechanism itself, specifically cross-attention.
Right.
Now, usually in attention, you have your queries, keys, and values. In GeoThinker, the visual tokens, the semantic understanding of this patch of pixels is a bike, Those act as the query.
Okay, so the concept of the object itself initiates the request for more information.
Right, and the geometry features that output from the VGT encoder act as the key and the value.
So the model is using its semantic understanding to query the geometry. It's effectively asking, okay, I see a bike here. Give me the 3D structure for just this bike.
That's it. It's clever, right? It flips the dependency. Instead of the geometry screaming at the model is politely asking the geometry for specific details.
I love that. And there's a critical constraint here, something they call frame-strict cross-attention.
Yes.
I saw that. Why is it so important to be frame-strict? Is this a video thing?
That's absolutely crucial for video. If you have, say, 32 frames of video, you don't want a visual token in frame 1 querying the geometry from frame 10.
That would break the spatial correspondence. You'd get temporal leakage.
Exactly. By locking the attention to the same frame, they made sure that token in frame 1 only pulls geometry from frame 1. It keeps the spatial reasoning clean and consistent over time.
Makes sense. It preserves the causal link between what you see now and the shape of it now.
Right.
But let's go back to that crowded bar analogy.
Sure.
You mentioned we don't need geometry for the walls and floors. Does SGF handle that on its own, or is the model still querying the geometry of the wall because it sees a wall?
That is where the second core component comes in. Importance gating. This is visually my favorite part of the paper. They added a really lightweight MLP, just a tiny neural network that looks at the image hidden states and predicts an important score.
So it's a filter.
It's a learnable filter. It outputs a sigmoid value, basically a probability between 0 and 1, that says, is this patch of the image important for geometry?
And this then acts the bias in the attention.
Yep. If the score is low, the geometry for a patch is suppressed.
And does it actually work? Or does it just learn to look at everything anyway?
Oh, it works. If you look at figure 4 in the paper, the heat maps are incredible. Without any explicit supervision, nobody told model look at edges. It naturally learned to highlight object boundaries, chair legs, and structural edges.
And what did it ignore?
It completely ignored the flat floor and the walls.
That is wild. It self-taught itself that flat surface equals boring geometry.
It's efficiency at its finest. It really proves the hypothesis that you don't need 3D data for everything to understand a scene. It just reduces that noise floor significantly.
It's learning an internal saliency map for 3D structures.
It's exactly.
There was one other component in the architecture that caught my eye, global scaling. They mentioned a scalar, alpha.
Right, a learnable scalar that initializes at 0. This is a classic stability trick you see in things like LoRa or other adapter methods.
That's to avoid shocking the system.
Right. It ensures that when you first start training, this new geometry injection doesn't just destroy the pre-trained weights. It starts at 0. So the model behaves exactly like the base LLM, and then it slowly ramps up as the model learns how to actually use the new data.
A smooth integration. Okay, so for the engineers planning to implement this, you don't just apply this everywhere, right? I imagine dumping this into every single layer of a massive LLM would be slow and maybe counterproductive.
You hit the nail on the head. They did a really interesting ablation study on layer selection, and they found that if you put this fusion block in the early layers, it actually hurts performance.
Why is that? I would have thought early visual processing needs geometry the most.
It's a good thought, but you want the model to establish basic visual semantics first. You know, this is a blob, this is a cat.
Before you hit it with complex 3D normals.
Exactly. If you inject it too early, you corrupt that semantic formation. The model gets confused about what the object is because it's focusing too hard on its shape.
Okay, that makes sense. Establish identity, then morphology. But what was even more interesting is that you also can't put it in the late layers.
Right. And the reason there is fascinating. The final layers of an LLM are super specialized for next token prediction.
Just figuring out the text output, the end of sequence token.
Precisely. If you inject a bunch of geometric signal right at the end, it just confuses the text generation. The model might start hallucinating or just fail to finish its sentences because this geometry signal interferes with the linguistic signal.
So it disrupts the linguistic flow. It's like trying to do algebra while you're trying to conjugate a verb.
That's a great way to put it. So they found the sweet spot is the middle 50% of layers. They call this ratio rho equals 0.5.
So you let the model think with geometry during the reasoning phase, but keep the input and output clean.
The middle of the brain, so to speak.
I love it. Speaking of constraints, let's talk about video. Video inputs are enormous. How does GeoThinker handle 32 frames of geometry without melting a GPU?
They use a clever spatial compression strategy. They just employ a simple 2x2 pooling on the geometry features.
So they merge spatially contiguous patches.
Yep. And that significantly reduces the sequence length for the transformer to process.
Doesn't that hurt accuracy, though? I mean, usually pooling means losing detail. If I pool the pixels, I lose the edge.
You'd think so, but surprisingly no. Because of that importance gating we talked about, the model is already focusing on what matters.
Huh.
And because the token count drops, the GeoThinker 32-frame model actually has lower FLOP's floating point operations than the Qwen 2.5 VL7B baseline in some cases.
Wait, hold on. It's adding geometry data and it's more efficient?
In terms of the transformer pass FLOPs, yes, because of that token merging. It's a great example of how smarter data processing is just better than more data processing.
Okay, that's the how. Let's talk about the how good. The benchmarks. The paper leads with VSI-Bench.
Right, VSI-Bench, the Visual Spatial Intelligence Bench. This is the big one. GeoThinker, specifically the Qwen 3 VL8B version, hits a score of 72.6.
Can you contextualize that for me? Is 72.6 good?
It's excellent. The previous best open source model was Cambrian S7B, which is a very, very strong model. GeoThinker beats it comfortably. It also beats proprietary models on this specific benchmark.
Wow.
But what's even more impressive to me is the generalization. They trained it on 8 or 32 frames, but at inference time, they fed it 128 frames.
And it didn't just break.
It didn't break. In fact, on the VSI biased benchmark, it held the lead with a score of 68.1.
Okay, pause on VSI biased. I'm always suspicious these models are just memorizing text patterns.
Like, if the prompt says sofa and bike, the answer is usually left because of how people take photos.
Exactly that.
And that's exactly what VSI debias tests for. It removes those language shortcuts. The fact that GeoThinker scores 68.1 while the competitor, Cambrian, drops all the way to 59.9 proves it's actually looking at the geometry.
It's not guessing, it's seeing. It's checking the math of the scene.
That's right.
That's reassuring. No, the one that really made my jaw drop was the VSTI-Bench results. This is the spatial temporal one, right? Moving through space.
Yes, and this is where the gap is just massive. In the object relative position task, GeoThinker hit 93.6% accuracy.
93.6%. That sounds basically solved.
Well, to put that in perspective, human-level performance is roughly 97.5%.
So we are approaching human parity on this task.
We are. Meanwhile, GPT-4o, the giant proprietary model from OpenAI, scored 58.1%.
That is an absolute trouncing, 93 versus 58. Why is GPT-4o so bad at this?
It likely goes back to that passive fusion idea, or maybe a lack of explicit geometry integration entirely. GPT-4o is amazing at semantics, but without those clean, explicit 3D priors that GeoThinker pulls in, it's just guessing.
It's just guessing spatial relations based on 2D pixels.
Right. It struggles to understand depth and relative position in a consistent way when the camera moves. It's relying on pixel patterns, whereas GeoThinker essentially has a depth sensor telling it the ground truth.
Okay, that is a glowing endorsement for this active perception architecture. But there's usually a trade-off. We see it all the time. Catastrophic forgetting.
Right.
You teach the model geometry, and it forgets how to describe a cat video.
That's the task interference problem. And usually, yes, adding general video data hurts spatial performance or vice versa. But if you look at Table 3 in the paper, GeoThinker actually improves on general video benchmarks like Video ME and MV-Bench.
While maintaining those high spatial scores.
Exactly.
So it's having its cake and eating it too. How is that possible?
The active gating is likely the savior here. By filtering out the noise, it prevents the geometry training from corrupting the general visual features. It keeps the representations distinct but integrated.
So it's not overwriting the concept of cat with surface normal of fur.
Exactly. It's basically compartmentalizing the skills.
All right, benchmarks are great, but let's get practical. Section 6 of the paper covers downstream applications. Why does a robotics engineer care about this?
They should care a lot. They tested this on Robotics. The task is embodied, basically telling a robot, pick up the bottle to the left of the laptop.
High stakes if the robot grabs your coffee instead of the bottle.
Yeah, exactly. And GeoThinker showed a plus 1.66% improvement in average accuracy. But the key metric for me is the unseen split.
Compositional relations the model hadn't seen during training.
Right. And it improved by plus 3.89%.
Which implies it understands the concept of left of or behind rather than just memorizing a kitchen layout.
Correct. It's true spatial reasoning. You can rearrange the room and the model still works. And then there's autonomous driving with Navism.
This one scares me more than the robot.
Well, the results should make you feel safer. They integrated GeoThinker into the Wreck-It Drive framework and saw significant boosts in drivable area compliance.
Staying on the road.
And time to collision compliance.
So fewer simulated crashes.
Significantly fewer. And the logic holds up. If you understand the 3D geometry of the scene better, you can plan safer trajectories. It's not just answering a question A or B, it's literally steering the car to avoid an obstacle because it knows exactly where that obstacle is in 3D space.
That's the so what right there. It's not just about winning on a leaderboard, it's about not crashing the car. It's about operational safety.
And doing it efficiently. We touched on FLOPs earlier, but let's be really specific about the cost.
Right. Is this active perception slow? Is the latency going to kill my real-time application?
The Spatial-Grounded Fusion module itself adds less than 5% to the total FLOPs. It is extremely lightweight.
So the bottleneck is still the geometry encoder.
Right, the VGGT part that runs before everything else. But once you have those features, integrating them is cheap.
And compared to the baseline model?
The 8-frame model is the same speed as the baseline VG-LLM. But the 32-frame model, thanks to that spatial compression, is actually faster than the baseline.
So you get better performance, longer context, and faster inference.
It's a win-win-win.
It really seems like less is more is the theme here.
That is the perfect summary of this paper. Less is more. Don't give the model everything. Just give the model the ability to choose what it needs.
So what does this all mean for the future of multimodal LLMs? We've got this great paper, these impressive scores. Where do we go from here? Is spatial intelligence just solved?
No, not quite. There is still a gap. We mentioned that 93% on relative position, but on absolute distance estimation.
Like how many meters away is that wall?
Exactly. On that, GeoThinker scores 67.4 against a human level of 77.00.
So it knows the sofa is left of the bike, but not that it's 2 meters to the left.
Precisely. That precise metric depth is still a hard problem. But I think the most provocative takeaway from this paper is what we saw in those heat maps.
The self-supervised edge detection.
Yes. The model learned to look at structure without being told to. And this raises a huge question. If we let this active perception evolve, do we really need a separate geometry encoder like VGGT forever?
Oh, that's interesting. You mean the LLM could just do it all?
Right now, we rely on VGGT to give us the 3D cues.
Mm-hmm.
But if the LLM is already learning to query specific structural information, maybe eventually we can train the LLM to hallucinate accurate 3D structures solely from 2D demand.
We might be able to remove the crutch of the external encoder entirely.
That would be the ultimate efficiency. Just one model, dreaming in 3D, no external dependencies, just pure end-to-end learning.
It would be.
And thinking with geometry is the first real step I've seen that suggests that's actually possible. It bridges that gap between the semantic world of LLMs and the metric world of robotics.
Well, on that mind-bending note, we're going to wrap it up. For all the ML engineers listening, the code is linked in the description. Go check out the GitHub, maybe run those turn right, move forward, logic tests yourself, and see if you can break it.
And definitely look at those heat maps in Figure 4. They are a thing of beauty.
Thanks for listening to this episode of AI Paper Podcasts. We'll catch you on the next one.
See you then.